Bismillahirrahmanirrahim. Assalamu alaikum dear students, welcome back in lecture 02 part example 03. So this is all about example 03 and we will cover this example in SI units. So this example is interesting because we will cover this in the units of MPa, which having different formulas as compared to US customary unit system. Design a rectangular singly reinforced. Let me write down the data, because first thing first, you must write down data. We have a rectangular singly reinforced flexure member. This point is very important. Singly reinforced section means that we have to provide steel reinforcement only in one zone, that is my tension zone, right? So that's why this is called singly reinforced section. Sometime if you see in doubly reinforced section, we will provide steel reinforcement in compression region, while if we provide only reinforcement in the tension zone, this is called singly reinforced section. We have a flexure member, right? A bending member to be used as an interior simply supported. This point is important. It is a simply supported short beam. We have longer beam, we have shorter beam. I will explain this. The slab system has a longer span of 5 meter and a shorter span of 3.5 meter, right? Factor slab load is 10 kilonewton per square meter. This is important. Factored slab load. Factor means this is all about WU, which is 10 kilonewton per square meter, right? We don't need to multiply the factors. Factor load is already given to us, and this includes the service live load and dead load, right? FC prime is given, that is 17.25 MPa, which is round about 2500 psi, and FY300 MPa, which is 40 KSI steel, right? Select SI reinforcing bars. So you will see how SI reinforcing bars differ from US bars, and keep the width of member equal to 228 millimeter. Width of the section is given, which is 228 millimeter. Architecturally, maximum permitted depth is this is all about the HA, which is 375 millimeter. This is important. We can't increase the depth from this depth, right? This is important. Now, first of all, we explain this diagram. We have already covered this part in, I think so, in part lecture 02 part 8 or 9. So we can see here we have longer beam right here and we have shorter beam. So we have to design this shorter beam having a span of 3.5 meter, right? And the longer beam span is 5 meter. This is important, right? So we will find out the equivalent slab width for this because we have interior short beam. So for interior short beam, I think so the equivalent width of the slab is 2/3 of LX. This is a member, right? We will use this formula. This thing is important, and this diagram is important. You can see this chart, this table. This is my SI designation of bars, and this is my US designation of bars. So the first one is number 2. Although number 2 bar is available in market, right? But in ACI code, this bar is not used. Similarly, we start from number 3. This is my number 3 bar. Remember, these bars are in millimeter. These all bars are in millimeter. So this is number 3. I think so. In 1 inch we have, in our local language we call this sutar. So 3 millimeter, sorry, number 3 means almost in 1 inch we have 25.4 millimeter roundabout, right? So in 1 inch we have 8 divisions or 8 numbers, right? So 1 inch equals to 8 numbers, right? 8 numbers or 8 sutars, right? So therefore if we find in one number, it is round about 3.17 millimeter in one sutar or in one number. So almost these numbers are rounded, like you can see here. Number 3 equals to 10 mm. This is rounded. Similarly, because if you multiply 3 with 3.7, roundabout we got 9.75. so this is rounded to 10 mm, right? Similar, number 4, it is round about 12 point something, which is rounded to 13. Similarly 5, 15 point something, it is rounded to 16. Number 6 equals to 19 mm. Number 7 equals to 22 mm. Number 8, 25, and this is the way. And these are the diameters of these bars in millimeter. These are the cross-sectional areas in millimeter, and these are the watts. So this table is very important to understand if you are converting from US to SI or SI to US. This is important. Next thing, this is important. This I have discussed this in my previous parts in lecture 02, in parts 4, 5, 6, right? How to fix the width of the beam. The width of the beam is taken L by 15 to L by 20, but the most economical width is L by 18. Similarly, the depth of the beam, the economical range of the depth of the beam is L by 12, right? This is important. From deflection criteria, we have discussed this how in previous part, that how to fix the depth of the beam from various criteria. So here is my beam and here is my grade of steel. So I have 300 grade of steel. So for the case of simply supported beam, the minimum depth of the beam will be L by 20, right? So this is my all about these things are important to share with you people. So let's start this solution. Now first of all, we need, although in previous example I don't consider the self weight of the beam, let me calculate the approximate self weight of beam. This is important. You will understand how to include the self weight of the beam. The service dead load of beam per running meter, right? The equation will be like this. The density of RCC, which is 2400 kg per cubic meter, times the width of the beam. Width of the beam is already given. If it is not given, it will be taken as L by 18, right? Although in this example we have given that is 228 millimeter, but if it is not given, here we will use L by 18. But I'm ignoring this one because the width of the beam is given, right? Here the width of the beam is given, so that's why 228 divided by 1000 to convert it into meter, times, as the depth of the beam is not given to us, so that's why we will use the economical depth of the beam, that is L by 12. My L is 3.8. It is given to me, sorry, 3.5. 3.5 divided by this is in meter, right? So divide by 12. 12 means L by 12. We will use this. This is the economical depth. multiply by 9.81 to convert into newtons, divide by 1000 to convert into kilonewton, right? So from this we got 1.57 kilonewton per meter, right? We are considering 1 meter length of the beam, not taking the total length of the beam, right? We are just considering 1 unit length. So if we factored this load, so the factored did load of beam, so 1.2 times 1.57, and we got 1.88 kilonewton per meter. Now we need to find the equivalent width, right? So my equivalent width of slab, right, which contribute load to the beam, right? Equivalent width of slab for beam 1, right? As I have already discussed this here, this beam. So we have two triangular areas and we will need to find out the equivalent width. We have already discussed and derived the equation for equivalent width. Please go and watch lecture 02, part 08 or 09. I have derived this equation. In this case, for B1, the equivalent width as my Ly equals to 5 meter and my Lx equals to 3.5 meter. So the equivalent width of slab will be 2/3 of Lx, right? So from this 2/3 times Lx is 3.5 meter and I got 2.34 meter. This will be the equivalent width, right? And we will multiply now because we have to find out the total factor load. So total factor load which is WU will be 2.34 times unit load. I have already discussed that we will multiply the equivalent width with the unit load, which we calculate kilonewton per square meter, and it is given to us that is 10 kilonewton per square meter. So we have to multiply this with that load plus the load of the beam 1.88. From this I got 25.3 kilonewton per meter, right? This is my WU right now, right? So this is important. Now I have a simply supported beam and the UDL, the equivalent UDL is 25.3 kilonewton per meter and the span is 3.5 meter, and we know the bending moment for a simply supported beam, the maximum bending moment WL square divided by 8. It will be multiplied with 1000 to convert it into millimeter if it is needed, right? So let me calculate MU. So my MU equals to 38.7. Now be careful this value, right? This is important. We will write this 38.74 into 10 की power 3 Newton meter, right? This is important. Now let me find out the H minimum. We know the H minimum from my previous section, as we have already discussed this equation, which is D minimum. Let's say we are using single layer of reinforcement, so then we have to add 60 millimeter. If we are using double layer reinforcement, then we will use 75 millimeter. I have discussed this in my previous parts. So my H minimum this time, my D minimum equation, a well-known equation, I have already derived this equation, 0.205 FC prime into B plus 60. Now if I plug all the values, be careful about the units. This is important. My mu value is 38.74 into 10 to the power 3 Newton meter. This is important. Now 0.205, I have my MPa, means if you convert MPa to Newton, we have to split 10 to the power 6. Now this becomes Newton per meter square, right, times the width of the section. So all the units in meter, so my width is 228 millimeter, so 228 divided by 1000, right, to convert this into meter. So this is the way how you can play with units. This is important. You must consistent with units. This meter goes with this meter, and this Newton will cancel with this meter, and this meter will be shifted to the top, right? This meter will be shifted to the top, and it will be here, and this square will goes with this square, right? So the answer will be in meter from this equation, right? So from this and adding, we have to multiply then the value which we got from this part, we will multiply this with 1000 to convert them into millimeter, because this is in millimeter, right? So the value, I think so 219, we got 219 or 0.219 we got from this. We will multiply that value with 1000, we got 219. So 219 will be adding with this 60. The final answer from this whole part will be 279.2 something, but ignoring 0.2, and we will use H minimum will be, my H minimum will be 279. If I use the deflection criteria, as we have already discussed this in the beginning of this lecture, this is my coefficient, right? So let me write down here my H minimum from deflection criteria is L by 20 times 1000. To convert it into millimeter, my L is 3.5 meter, so from this I got 175 millimeter, which is less than the previously calculated value. Now maximum architectural depth, my architectural depth which is already given to me, that is HA, is a 375 mm. I can't increase my depth from this value. So, and the most economical depth, right, most economical depth, that is which is used H economical, which is used L by 12 times 1000. From this I got 292 mm. So the selected depth, let's say this is from this I got 292, from this I got 175, so I ignore this one. I can't increase my depth from 375, and from here I got 279. So let's say I'm using my depth my final depth is, let's say I'm using 300 millimeter, right? This is my final depth because it is close to this one. So although this depth is less than HA, right? So this is my final depth. Now I am calculating the row minimum value, which we will use in the coming section. If you remember, my row minimum in US customary system, that is 3 times FC prime divided by Fy should be greater than or equal to 200 divided by Fy, but this is in US system. In a SI system, it is 0.25 times of FC prime divided by Fy greater than or equal to 1.4 divided by Fy. Remember, when the FC prime is less than or equal to 31 MPa, this is the governing part. We will ignore this one and we will consider this part, because always this part is giving me the greater value as compared to this one. So that's why row minimum equals to 1.4 divided by Fy, that is 300 MPa. So this will give me 0.00467, right? Sometime we multiply this with B and D. So if we multiply this portion or this portion with B and D, it will give me area of steel. Then this row will be AS, right? So this is my row minimum, and my row max I have already derived this equation. My row max will be 0.85 beta 1 FC prime divided by Fy into 3 by 8, right? If I'm assuming that my epsilon T is 0.005, so on the basis of this I got 3 by 8. I have derived this in my previous part. From this I got the value of my maximum steel ratio 0.10156, right? This is my row max. Now we will calculate the area of steel, which is the target section. Now area of steel, we can use different method: trial and error method, direct method, tabular method, graphical method, approximate method. We have number of methods, around about 5 methods. Let's say we are using trial and error method. In example number 1, I have used all the methods, but this I am using direct method and only trial and error method. So from trial and error method, let's say I'm assuming A equals to D by 3 or 0.2 times our depth. So from this my effective depth will be 240 divided by 3. Now how I got my D? So you must know that my D is H minus 60. So from this I got 240 millimeter because my H is 300. Now from this I got the A value, that is 80 millimeter, right? Now my area of steel, this is trial number 1. My area of steel, that is from MU divided by, so from this I got 717 millimeter square, right? So this is my first trial. Let me repeat the second trial, trial number 2. I revise my A value. I will calculate the actual value 0.85 FC prime into B. So from this I got the A value 64 mm. And again recalculate the area of steel by using this equation. I have, let me put the value 74 times 10 to the power 6 Newton in meter, right? And here I have 0.9 times 300 MPa. Sorry, not this 0. 300 MPa times 240 minus 64, right? So 64 divided by 2, because I got here 64, that's why 64. So it will give me 690 millimeter square. This is my second trial. So there is huge difference between these two values. Let me go for another trial, that is trial number 3, FC prime into B. This time my area of steel will be this one, 690. It will give me 62 millimeter. Now you can see this value is close to 64. So that's why the results is coinciding, right? Area of steel from the same equation, if you plug the value, you got 687 millimeter square, and this time this value is close to previously calculated value. And here my final area of steel is 687 millimeter square. We can go for other trials, and you can see at 5th or 6th trial this value will be closed, right? So this is one way that you can calculate. We can use the direct. I always prefer this equation because this is time saving equation. If I use my calculator, so if you plug all the values in this equation, make sure you will be consistent with units, and right, the D value is 200 to 240, the B value is 228, FC prime is 17.25 MPa, 300 MPa, and D similarly 240 square. Make sure you will plug this value 38.74 times 10 to the power 6. Similar, this is 17.25 and this is 228 millimeter, right? So units will be here in millimeter. Now you got the final value of area of steel is 685. This is the exact value, right? 685.75 millimeter square. This is the exact amount of area of steel. Remember, this one value is 687. If you go for 4th to 5th trials, you will find this value, right? This value is 685.75. So this is my exact value. And so if I use this 19 mm bar and this 16 mm bar, right? This 16 mm bar, if I use two 19 bars, two number 19 bars, it will give me an area of steel 2 times the area of 19 bar, that is 284. It will give me an area of 568 millimeter square. And if I use one number 16 bar, it will give me an area of steel which is already given here. This one, it is 199 millimeter square. So the total area will be the total area of 219 mm bar plus 1 16 mm bar, it will give me 697 millimeter square, right? So this is my final, because it is close to my calculated value, that is 685.75 mm square. So this is my final bars arrangement, right? So to cover this area, what bar we will use? 219 number 19 bar SI designation, and 1 number 16 bar. This is SI designation bar, right? This will give me an area of steel which is equal to 697 millimeter square, right? Now the cross section of the section will be 1 bar in the corner. Here in the corner there are 2 number, and here we have 1 smaller bar. So these 2 bars are 2 number 19 SI designation bars, SI, and this bar is number 16, 1 number 16 SI bars, right? This is my final section, right? This is the total depth of the section, and the effective depth of this section is 240 mm. The final depth of the section is 300 millimeter, and remember this bar should be bent up, so it will be showing like this, and we will use a stirrup of we will use 2 hanger bar. These hanger bars will be 2 number 16, right? SI. These are the hanger bars, not taken in calculation. And if we draw the longitudinal section of these bars to show the bent up and cut up position, now you can see this is my hanger bars, 2 number 16, right? And here I have 2 in this location, right? The section will be different in this location. Here I have 3 number 16, right? And here I have the section at the mid. Here I have 2 number 19 and 1 number 16, and this bar is bent up at a distance of ln by 7, right? ln by 7. Make sure the supports is 228 millimeter, right? The clear span, this is important, right? This is important. The clear span will be, because the center to center spacing is 3.5 meter. If we subtract half of this and half of that, so I got 3500 minus 228 divided by 2, half of this bearing support minus half of the second support. So the clear span will be 322.72 millimeter. This is my clear span. So this ln will be this one, right? In millimeter, right? It will be bent to the top, and I will use stirrups So stirrups will be continued to the support, and the stirrup will be number 10 or number 3 at the rate of 150 millimeter center to center. These are assumed, right? Similarly here 2 bar will be continued, right? This is 2 number 19 bar here, and here 2 number 19 bar will be continued, because we have to continue 50% of reinforcement, or 2 bars must be continued. This is a code criteria. I have uploaded so many lectures over this, right? So we have to continue 50% reinforcement of the positive section, and minimum 2 bars must be continued. We bent 1 bar, which is 1 number 16 bar. We bend that bar, and the rest of the bar is extending towards the support. So this is all about the detailing, that how we can detail this, right? But make sure the section is different at the mid and the section is different at the right. So we have 2 sections, section AA and section BB, right? The section which we draw here, this is at section BB, right? This is at section BB, while the section at the support, it will be different. At the support, the section will be different from the mid section, right? We have only 2 bars, and in the top we have 3 bars, right? This is important. Here this we have 3 number 16 bar right here, while here we have 2 number 19 bars. This section is at AA. So this is important to understand, right? And this is number 10 stirrup at the rate of 150 millimeter center to center. Similarly here. And if we calculate the spacing, right? If we calculate the spacing between the bars, so the spacing will be, the width is 228 millimeter. We have 2 clear cover will be 40 millimeter in this case, minus clear side cover, minus 2 times we have stirrup number 10 mm, minus we have 2 19 bars, minus we have 1 16 bars, or 16 bars, and divide this by the number of spacing. We have 2 number of spacing. So from this, if I use my calculator, I got this from this is 37 mm. So this distance is greater than the maximum bar diameter, that is 19 mm. So the spacing will be okay. Need to calculate the ductility check. So rho is we have area of steel now. So we need to calculate area of steel. So the area of steel, as we calculated, this is 697 divided by BD. So B is 228 times D is 240. So from this, I got the value of 0.0127, as this is greater than rho minimum, because rho minimum is 0.004 something. So this is greater than the, so this is okay, and it is also less than rho max. The rho max value is 0.0156. So ductility check is okay, and we can also review the same problem for epsilon s. As we can see here, epsilon s will be equals to epsilon t because we have one layer of reinforcement. And if we calculate the A value, this time I will use the exact amount of steel, right? 697, right? And we are assuming that, let's say, Fs equals to Fy, right? So let me calculate the A value. I got the value of A, that is 62.547, right? 547 millimeter. And the C value will be A divided by beta 1. So 0.85, I divide this, so this is 73.585. Now I calculate the epsilon s value, which is equals to epsilon t, so d minus c divided by c into epsilon u. So my d value is 240 minus 585 divided by 73.585 times 0.003, and here I got 0.00678, which is a good news for us because it is greater than 0.005, and that's why this means what our assumption is right. F is equals to Fy. Steel is yielding and as epsilon t is greater than 0.005, so that's why P can be used as 0.9. So this is good news because we don't need to adjust the phi factor. The advantage of D minimum equation which we used, right, 0.205 Fc prime into B, this is the advantage, right? If you fix the diff from this equation, you don't need to adjust your phi factor, right? This is the beauty and advantage of this equation. Now we can find out the MD value. So MD value is 0.9 times your Fy times your area of steel times D minus A over 2. So make sure you should be consistent with units, right? If you are plugging the values, let me write down because this is the important point. 0.9 times Fy is 300 MPa, right? MPa. So that why we MPa means mega Newton per square meter. So this is important. We have to convert meter to millimeter, right? We have to convert meter to millimeter because here I am using 697 millimeter square, right? And similarly the D value will be in millimeter, that is 240. The A value is 62.547 divided by 2. So this is also in millimeter, but this value is in meter, square meter. So I need to convert this into millimeter square. So that's why I will divide it by 1000 square to convert this, because this is in MPa. So this means what? Means that mega Newton divided by meter square. So to convert it from meter to millimeter, we know that 1 meter equals to 1000 millimeter. So 1000 square, right? So it will give me a value of 39.28. My design strength or design capacity of the section is 39.28. Now this is the way I have write down here that the unit which we got here from the above calculation, from this calculation, the unit will be mega Newton millimeter. Now we convert this into kilonewton meter. So how to convert this, we just take this. Mega means 10 to the power 6, Newton meter, so we need to convert this millimeter to meter, so we need to divide this by 1000, and we split this 10 to the power 6 into two parts, 10 to the power 3, 10 to the power 3, and we write 1000 in the form of 10 to the power 3. This 10 to the power 3 cancel with this 10 to the power 3, and this 10 to the power 3 means kilo, so the final unit will be kilonewton meter, and we need this one, as this is the design capacity. This is the design capacity of our section. This is the design capacity of our section, which is more than the MU, right? 38 point, and you can see the clear difference. There is a little bit difference. Both the values are close, so this is an economical design. Always try to find the design capacity which is close to the acting loading or moment. So this makes your design economical, right? So this is page, as you can see here, this whole page is my review section, while the previous pages, this is my detailing section, and this one is also the designs design section, and similarly this is also my design section. So this ends up this example here with complete design and review. Thank you for watching. See you in next lecture.